Hi everyone. So today we will be learning about entropy. So when we think of entropy, we the first thing that should come in our mind is the word disorder and random. It's the disorderness. It's the disorderness or the randomness. So entropy, denoted by S, is a thermodynamic property that is a measure of a system's thermal energy per unit temperature. So when we talk about entropy, it simply means that it's the measurement of thermal energy caused by, of course, the temperature. So in other words, it's a measure of the randomness or disorder of the system. So this thermodynamic property, as I highlighted here, is a measure of how much energy is unavailable for conversion into work. How much energy is available for conversion to work. The more random or disorder a system is, the greater the entropy. So, with this being said, entropy doesn't need energy, okay? Since it's a spontaneous process. It's a spontaneous process. So, if you have read your module or um, even scanned the illustrations there, we explained spontaneous processes and non-spontaneous processes clearly. So spontaneous processes doesn't need um, energy energy or force exerted for it to happen. So the first image here shows that the ball will roll down even without an effort or energy of the person, while non-spontaneous processes requires a push. Non-spontaneous requires energy for the conversion or for the reaction to happen. So that's the difference between spontaneous and non-spontaneous processes. So back to entropy. Um, Entropy is a spontaneous process, meaning it doesn't require energy for the reaction to happen or the conversion to work. So since entropy, like enthalpy, is a state function, it is independent of the path or route taken in returning the final state. So if you compare um, the formulas for entropy, so enthalpy, if you recall, enthalpy denoted by H. When we talk about the change in enthalpy, we add the triangle delta here. And for the entropy, this HR enthalpy, for the entropy we have S. If um, if we want to see the change, we add the triangle. We have change in entropy. And if they are on the standard state, we have standard state. The standard state for S is the temperature is at 25 degrees Celsius. So we add the degrees here, meaning that we want to see the standard change of entropy, or we want to see the standard change of enthalpy. So we add the degrees symbol as a superscript. So therefore, the change in entropy depends only on the entropies of the final and initial states of the system. So when we talk about final, we talk about products, right? And the initial as the reactants. So a positive value of standard entropy indicates that the final state is more random or disordered than the initial state. This is simple to understand. So if you have a greater than 0, a positive value for the entropy change, it states that the final state, the product state, is even more random than the initial state or the reactants. So a negative, of course, means that the final state is more ordered. It is uniform. It doesn't really change anything. It's a non-spontaneous phase than the initial state. So, the last note here is that spontaneity of a process is not solely determined by the tendency of a system to proceed at a state of lower energy. It is also dependent on the state of disorder. So since spontaneity is of low energy requirement, it is not only that, it also depends on the state of disorderness, randomness. Okay, to better illustrate what these texts mean, so we have an example here. We actually have two examples. So the instruction here is to calculate the standard entropy change. Standard entropy change. So since it's a standard, we're assuming that the temperature is at 25 degrees Celsius. For the following reactions, using a given standard values and figure out if the resulting values obtained are consistent with the expected entropy change as predicted qualitatively. So it basically means that we should solve the standard entropy change for these reactions. So then later part, if it's positive, we'll note that it has an increase in entropy, and it's negative, it's decrease in entropy, meaning that it's more ordered, and the former part is more disorder. So first, we should know, this is already in your textbooks or in your modules, that the solution for this is this one. This change, the standard entropy change is equal to the summation of the Y standard entropy of the product minus the summation of the Z standard entropy of the reactants. So the Y and Z here are actually the coefficients or moles, the moles of our reaction. So we have to make sure that our equation is balanced first. So summation, it means that all components here should be added up before we subtract another components from the reactants. So first, we know that the product side contains NaNO2 in solid and oxygen gas. So first, we know that the product contains the standard entropy of NaNO2 plus the standard entropy of O2 minus, we know that this is the product and this is the reactant, right? So the reactant side, we only have one component. We have standard entropy of NaNO3. Now, do not forget to multiply the number of moles here. So for the product side, we have 2 times, it's 2 mole. Let me add the unit, 2 mole of NaNO2, the standard entropy of NaNO2, which is 103.8 joules per mole to Kelvin. It's the temperature in Kelvin, plus the 1 mole of oxygen and its standard entropy, which is 205 joule per mole to Kelvin, minus the standard entropy of NaNO3, which has 2 mole of it. We look at the reactant side, times 116.5 joules per mole to Kelvin. So when you use your calculator, correct me if I'm wrong, we have 412.6 joule per Kelvin. The mole are cancelled. So minus here, the mole is also cancelled. Have 233 joule per Kelvin. And it's a positive 179.6 joule per Kelvin entropy. Standard change of entropy. So it has an increase in entropy. So this means that since it's greater than 0, it's positive. It means that the reactant side, the product side here, NaNO3, is more disordered than the reactant side. So, no, let me paraphrase that. The product side is more disordered than the reactant side. That's what it means. So for the next example, we have the synthesis of ammonia from nitrogen gas and hydrogen gas. So the product here is in the side 2NH3, it's the ammonia, and we have the reactants, nitrogen gas and hydrogen gas. So we have given values, standard ones, and let's solve again. So we have standard change of entropy equal to the summation of y entropy change of the products minus summation of z entropy change of the reactants. Then we know that the products contain entropy change of NH3 minus the entropy change of nitrogen gas plus the entropy change of hydrogen gas. So let's not forget about the moles. So for the product side, we have 2 moles of NH3. So 2 mole of NH3 times the given value for NH3, which is 192.8 joule per mole Kelvin, minus entropy change of the mole for N2 is 1 mole of N2. Oh no, let's just leave it as 1 mole of N2 times the entropy change of N2, which is 191.6 joule per mole per Kelvin, plus the mole of hydrogen gas, which is 3 mole of hydrogen gas, plus the given entropy change of hydrogen gas, 130.7 joule mole Kelvin. So when we cancel out the moles, we have 385. It's 385.6 joule per Kelvin minus 191.6 joules per Kelvin plus 392.1 joules per Kelvin. If you use your calculator, we would get negative 198.1 joules per Kelvin. So this one is negative. Then we conclude that there is a decrease in entropy, implying that the product side of the reaction NH3 is not that disordered or random. It's more ordered than the reactant side. So I hope that's clear. Thank you for watching.